It's like an old computer disk. So what we've got here in example problem 14.3 for our unit on rotation is we've got a computer hard drive disk. And HDDs, these computer hard drive disks, what they are essentially disks inside a platter system that are spinning around. And they're spinning around extremely fast. They're spinning around like easily 7,200 revolutions per minute. To give you an idea, if you look at like your car, whenever you look at your gauge that says your RPMs, your revolutions per minute, if you're up into like the 7,000, your engine is like, wah! It's like going ballistic. And once you hit that like 8 and 9, normally it turns like the meter goes red, and it's like, what are you doing up here? Why don't you shift? Have you ever used a manual before? And hopefully we don't have to deal with that because most of us have automatics here in America because we like automatics for some reason. But these computer hard drives are spinning extremely fast, okay? We've actually started to move away from hard drives, and we've started to move into solid-state drives, SSDs. These don't spin in the same way, but they're more expensive. So let's talk about the old-school hard drives that you probably still have in your computer. These hard drives have a diameter of 3.5 inches, okay? So that's a diameter there. Let's just star that for a second. And that's in inches. That's garbage. We're going to have to convert that. Let's just note this conversion here. And they rotate at 7,200 RPM. And that's revolutions or rotations per minute, okay? So that's 7,200 revolutions per 1 minute. Now, the read head, the actual piece that does the reading off of the hard disk platter, is positioned exactly halfway from the axis of rotation to the outer edge of the disk. What we're looking for is the tangential speed, so that's a linear velocity, that is a v. We're looking for v here, in meters per second, so we got to do that conversion, of the disk under the read head. And these read heads can move in order to read different parts of the disk, but just at this halfway point, what do we have? So we've got some conversions to do here, and let's also just note this. If we draw a little picture of the hard disk, it is just a circle. This diameter was 3.5 inches or 8.89 centimeters. That means if we cut this in half, this radius is 8.89 divided by 2, which if we just run 8.89 divided by 2, we're going to get 4.445 centimeters. Now, what we want here is that the read head is positioned halfway from the axis of rotation to the outer edge of the disk. Well, if this center here is the axis of rotation, and this is the outer edge of the disk, where the read head actually is right here. And that means that our actual distance of how far we are away from that axis, this right here, is half of the radius, or 1/4 of the diameter. So this value of r we are looking for is and it's technically 2225. Let's just call it 2.2 centimeters, which if we wanted to convert into meters, we would divide that by 100 or move that decimal 2 to the left, so to get 0.022 meters. That's our actual value there. That's, if this entire meter stick is the disk spinning around, this is the radius from the center out, and then we want half of that, so that is our R value. That's what we're actually looking for, okay? Now, if we want to figure out what this linear or tangential speed is, that linear tangential velocity, then one way we do this is we say that the linear velocity is equal to the angular velocity multiplied by some radial position, or how far away you are from that axis of rotation. Luckily for us, we have the r value. It's 0.022 meters. That's great. However, our current angular velocity is in this weird 7,200 revolutions per minute. I need to get it into radians per second. We know radians isn't a physical unit, so if we're able to go down here and write out the radians per second multiplied by meters, that's going to give us just meters per second, because rad meters aren't a thing. So we need to get this angular velocity from revolutions per minute into radians per second. So a little fence post, train tracks, dimensional analysis, whatever you'd like to call it. We know that there are 2 pi radians in 1 revolution. The angle of going around 1 complete circle is 2 pi radians. And this is nice because we see now our revolutions simply go away. They've divided out. Well, we also have minutes in the denominator, and I don't want minutes in the denominator. I want seconds in the denominator. Well, if I want to say conversions between seconds and minute, I can say that 1 minute is 60 seconds. Ka-ching, ka-ching. Now the minutes have gone away. My only units I'm left with are radians per second, and this will be a very nice value for us to use as omega down below. When you're solving for omega here, while we could leave things in terms of pi, we might as well just multiply by the pi now, because when we convert to a linear or a tangential speed, we don't want pi's in that anyways. So make sure when you're multiplying this, you're doing the 7,200 times 2 times pi, and then divide that by 60. When we do this, we should get a value of 750, let's just round it up to 754 radians per second. It's really 753.9822369, but numbers are the worst, aren't they? So let's just call it 754 radians per second. So now when we go down here, we can actually solve this out. We can say here that our linear or our tangential velocity is equal to the 754 radians per second multiplied by that radial distance from the axis of rotation, 0.022 meters. We've already seen above that, our units are going to be these radian meters per second, but the radians don't carry through, so they're just meters per second, which is very nice for us. And we find that our linear speed here is just 754 times 0.022. We get 16.5 meters per second. So nothing too crazy here. This problem wasn't actually a lot of kinematics or rotational kinematics. It was really just a conversion. We knew information about the disk rotating and its rotational speeds. We just wanted to figure out if we converted that rotational speed into a linear speed at that point, what would it be? Remember, because this was at a point halfway between the axis and the outer edge, that is specifically the angular or the linear speed right here. If we moved further out towards the edge, we'd be going faster because we'd have to cover more distance in that same amount of time as it's rotating around. And if we moved inward, that linear speed would become less because there's less distance. There's a smaller circle on the inside that this has to make as it goes around. But in every single location, all the way here and throughout, the angular velocity is the same. That angular velocity is the same everywhere, just that r value changes. So with that, this little problem here is finished. We're going to try out one more of these, and until then, adios, and take it easy.